My name is Raphaël. I'm a lead data scientist in a Paris-based company in France. So we mostly do computer vision. So I've been for the past year a Keras and TensorFlow contributor, and I've built TF Explain because there was like no specific libraries to for interpretability, and I wanted like to be accessible to most users. So what is interpretability? So when you start, for example, if you load the iris datasets and you want to train linear regression on it, you can like easily find what are your parameters and how the model behave compared to the dataset. What are the important features? And it's kind of a white box because you can really understand and take a deep look at what is happening, what are the features that are important. There are limited numbers of parameters, so you can really understand what the model is doing and explain its decision. But the problem is that when it comes to more large networks with millions of parameters, how do you do that? How you have some multiple convolutional filters which applies to the whole image. How can you know which activations are the most important for your output decision? How do you just explain? Okay, my deep learning models is predicting it's a cat. What in the image is actually what's important to predict the cat? Is it really focusing on the cat and not on some bias in the rest of the image? So that's what interpretability is. It's mostly giving an input, giving an explanation on what is important for the model to take the decision. So basically, it's mostly for computer vision salience maps, which means you visualize on the input what's important for the decision. So the more important the zone, the color map will like translate this phenomena, and you will just have some hot regions in yellow and cold regions in blue. So before going in, I will take a bit about TensorFlow 2 release because, and mostly I'll focus on the training parts because it will help you understand and make sure you're at ease for the rest of the presentations. So the main change is that Keras has been the major API for TensorFlow. You have 3 different levels depending on what are your needs. So it goes from the sequential API, which helps build linear models where the output of the previous layer will be passed as the input of the next one. There is this functional API, which is a little more complex, but which helps to build non-linear models. For example, if you have some residual connections. And then there is this subclassing API, which is like a lot like PyTorch implementation, where you can define a class, define all the variables, the layers you have in it, and then apply the logic as you want in a forward pass. Okay, so we'll talk about the first 2 APIs and the training process in those APIs. So when you start a layer, so the first step is to load the sample data. So you just have some tensors. You build a model by stacking linearly in a list your layers. So for example, here we have just a global average pooling and then a dense layer. And you specify the input shape to the first layers. So for example, here we have images of 28 by 28 and three channels. And we just want to take a binary decision on it. Then you just compile it with specifying a loss and an optimizer. Eventually, you can define some metrics you want to to get during the training process, and then you can fit it on your data to train the model. So the output, this kind of graph you create of models, it's in the top right corner. It's purely linear graphs. So the output of first layer is the input to the second layer, and you can't have more subtle architectures than that with this API. So there is this functional APIs that allows us to go with different architectures. For example, to implement residual connections. So you still have the same idea of you load the data and then you define your model. And the definition of your model is you take an input, you specify the input, and you apply all the layers to variables, and you take the output you take in other variables. So you can play and specify the inputs to a specific layer. So for example, here we save the inputs in an input variable, so we can pass it to the add layer later and create the residual connections. So it allows, in most cases I've seen for production, simple models, it's enough to build most models if you're not building some kind of specific penalization, regularizations. It's clearly enough for you to get started. And then you still have this compile and fitting, which remain the same between the APIs. Okay, so now the other point I wanted to show you is how you can get gradients with the Tensorflow 2 release. So in the 1.14 version, for example, you had to obtain those gradients, you have to just get the data, define some placeholders, define also all the graph you want to run, and you have this cost function that you pass inside a TF session. So basically, the computation of those variables were painful to have. You had to create sessions. You have to think about scope names. Does initialization of variables? It was pretty painful to debug because it was not executing eagerly, so you couldn't access variable values at runtime. So now they fixed a bit this behavior by enabling the eager execution. So now when you define your model and you apply it to a specific input, X and Y, you can have access directly to those values. So if you see, we use a gradient tape object, which has been introduced in this version. What it does, it records all operations that are done, and it helps to get the gradients on the operations that have been performed during this during the context. So you run all the necessary operations inside this context object, and then the tape.gradient methods contains all the gradients you can have on this graph, and then you can apply it to the model parameters with the optimizer apply gradients methods. Okay, so that was a pretty subset of what has changed in TensorFlow 2. There is a lot more to discover around eager execution, autograph, TF.function. There are also a whole ecosystem of libraries they've built for mobile devices, for production use, for scaling. So I've put on some additional resources. This is not exhaustive. You can clearly find a lot of stuff, good stuff, on the TensorFlow website. So I encourage you to visit it. So now I'm going to talk more on interpretability. And before we get started and dive into some methods that can be a bit like confusing and complex, what I wanted to present is tfexplain, which is a library that compiles a lot of those methods with a simple API. So you can basically use it every day without thinking about, okay, I have to build something really complex on my model and I don't want to. The idea is basically to make the user able to run without any effort some interpretability methods. So the important thing was to focus on the TensorFlow workflow. So one major thing is being able to visualize during training directly in TensorBoard what are the output maps, the saliency maps. So here you can see that we have run some methods on the model during training, and during training we can monitor if there are how the model is doing on the validation set, and we can directly confront some methods between them, see what are the outputs, if there are some biases that appears. So for now, there is seven. The slide is not up to date. 7 methods that are available. So you can directly compare methods. The idea is the problem of interpretability is that there is no official metrics to say, okay, this one is better than this one. A lot of research papers are just, okay, they give the methods to some users and get some feedback on it. So my advice on this is do not trust one method particularly and use different methods at the same time to confront them, to understand if they have the same opinion on the input, if they produce a similar saliency map, or if they just are going in the opposite directions. So you can just have some different judges on what the input is. Okay, so how to use tfexplain? There's two ways to do it. The first one is, let's say you have this model which is already pre-trained, for example, the VGG16, and you want to see how it performs. So you want to check, run some methods on some given inputs, and checks that the input, the saliency maps for this input is kind of logical. So you load the model and the validation data. You just instantiate the methods you want to use, and then you have for all methods implemented in tfexplain, you have this .explain entry points, which is the same, which always takes the validation data and the model to observe. And eventually, depending on the methods, some additional parameters you can tune, and then it directly saves the output of the algorithm as a PNG format, so you can observe directly the color, the saliency maps inside your computer. The other way to do this is, as I was explaining earlier, you want to monitor during training what is happening. So basically, you want to have a callback that after each epoch is running some methods, and you want to visualize during training how the output of these methods are going. So what you do is take a subset for a given, let's say a given class, and then you want to call a specific callback. Each method implemented in the library has its corresponding callback, so you can just, okay, let's say I want to use this method, okay, so I'll take its corresponding callback and pass it to the fit callbacks arguments. So now when the fit is running, it directly saves the output as a TensorBoard format, and you can just run TensorBoard and see what happens. So we've released the package in August, so you can check it. It's on PyPy. It's called TF-Explain. And now I'll just dive into some methods implemented in it. So you can just have some notions of what interpretability methods are. Because it's not only visualize the activations of convolutions, there are more to that, because visualizing activation helps to identify if kernels are kind of useless or are doing like something weird with the input, but it doesn't really give feedback on each importance of the features. So the first one we'll explore is called occlusion sensitivity. And the objective is to hide some parts of the image successively and just see if there is a drop in confidence on the output. Because what you want to say is, okay, if I hide some part of the image that makes a significant drop in the confidence, that must be because this particular part of the image must be important to the decision and must be important to the model to take its decision. So you just hide successively and build a heat map corresponding to the confidence outputted for this patched image. So basically what you want is just to create the patched image. So you apply some gray patch over a certain region. And for each patch, you'll predict with your model and take the target confidence of the predictions. And then you can create back a heat map with where you take 1 minus the confidence. Because if there is a drop, you want it to be something positive on the heat map. So the larger the drop, the bigger on the heat map. So this method has some problems because it's pretty inefficient. You have to run multiple predictions. You want to maybe make the patch size variable because sometimes it's going to be small features. Sometimes it's going to be a big one. So you can't have a really precise way to say, okay, this part of the image is important, and you have to merge some multiple outputs, multiple saliency maps with different patch sizes to build something you can really trust, and it's kind of computationally expensive. So people started to say, okay, we're on deep nets, everything is about gradients. They must have some kind of information on what are good features and bad features on the map, on the input. So what if we just look at the gradients? So what if we just look at what makes an input image a better cat, for example? There are some regions in the image that are already discriminative to be a cat, and the idea is that if those parts are really important, gradients will be larger than other, for example, the wall behind the cat. So what you get at the data on the output is a gray scale map, and the idea is where it's whiter, it means the features are more important to the networks and where the zones are gray. So the problem with that is that, okay, we'll just explore how to do it. So you load your sample image, you load your model, and you load what is the expected output you want. So for us, we just want it to be a cat, so we create a one-hot vector, and the loss will be the difference between the predictions and the actual one-hot encoded cat. And note that here we added a tape.watch on the input, because we want the gradients on the input and not on the model. So when you run this, you just get the gradients inside the tape.gradient object, and it's just simply the output map you want, the output saliency maps you want to visualize. So this has some major issues, because it's pretty open to interpretations. For example, if we see the saliency maps for the kite class when we predict a cat, it has some interesting features of a cat. For example, the nose, the ears. If you just like show the kite gradients to someone, it will say, okay, that explains a lot on the predictions. But the problem is that it's not exactly what is relevant. It should be the cat shouldn't appear on the gradients for the kite class. So this has raised some interest in how we check that an interpretability method is like relevant, is producing good examples, and is really explaining what the model is doing, and rather than just saying nonsense. So the first one is, okay, you have this model, and basically if you change some parameters in it, the output saliency map should change too. And the more you randomize some parameters, the more the saliency maps should do nonsense. And that's because if we really are observing the model, and if we really randomize a lot of parameters in it, the model shouldn't be able to predict anymore that it's a cat. So the explanation map for the cat shouldn't appear as it was at the beginning. And what's kind of warning in this parameters randomization is that some methods are actually kind of the same over the randomizations. So even with high proportion of randomized parameters, we can see that the heat maps, the saliency maps, stay the same. And that's because there's a lot of methods that depends on the input to provide an explanations. So what we see is that there is a lot more influence from the input than from the model itself on the output map, and that's why it's produce constant output, even if the model is completely nonsense. Okay, the other check is training a model with randomized data. We want to make sure that if the model is really explaining a class, if we randomize the label during training, the output map shouldn't learn something. The model shouldn't learn something, and it's not just switching labels between them. It's really randomizing some labels inside the dataset. So basically, if we randomize a high proportion of labels, the model will learn some noise over the data, so it shouldn't produce a saliency map that is corresponding to the one with true labels. So to conclude, we will explore one last method, which is called GradCam, which is based on the activation maps of the last layer of the network. So you take the last filters of your network before the dense layers, which activates a different region. And the idea is that those filters are the features to the dense layer. So you will get the decision of the dense layer based on those features. So if we can manage to ponderate those features to see what's the weight for each filter, we can induce like the region of the image that is important to the decision. So what we do to weight those filters is we take the gradients over those, and we're gonna spatially average the gradients, because if the gradients are high, have a high value for a given filter, it means it has more weights toward the final decision. So especially averaging the gradients help us build the final color map by weighting on the filters. So you take filter 1, you take the gradients for filter 1 towards the final decision. Is the gradients with high value or low value? And depending on that, you'll have those filters with a corresponding weight. Okay, if we'll look at the implementations, you want to build a subgraph that outputs both the last convolutional layer and the output. So when you run the predictions, you will get the output of the convolutions and the output of the layer. You will compute the loss, which is maximizing the prediction score for the cat. And then you'll just do this spatially averaging and do the weight average of the filters with respect to the weights of the gradients. And that's it, and that's how you get an output map, which is the size of the last convolutional outputs. So for example, for VGG, it's gonna be 14 by 14, but has the convolutions are taking spatially zones. You can deconstruct your 14 by 14 to the original image size. And the output for this, and what's why I consider it to be like one of the best options right now, it's that it's pretty much effective, because you do not have to backpropagate to all the model. You only have to backpropagate to the last convolutions, and you have some outputs that really respect this label check, which means that when you observe the output for the cat, it really is different from the kite class. And what we observe is that even for the kite one, the cat becomes a really cold zone, which means it identifies that features are not at all relevant to the kite, and they just make the confidence drop for this class. Okay, so my advice on this is really learn to, you have now, so you have now TF-explain, which helps use interpretability methods. My advice is when you use some, it's a nice step towards understanding neural networks, but please don't use only one, because interpretability methods have a high subjectivity in them. You want to be able to compare methods between them to make sure that they all agree on the decision, and you don't want to just trust one method blindly. Thank you. And if there are some questions, I'll be happy to answer it. Okay, thank you.